Hello everybody, today we're going to be doing a gentle intro to deep learning with applications. I'm going to be talking about some of the applications that I've worked on myself, and then I'll show some other applications that I've able to everybody, and then we will dive into some of the concepts behind it. So the first application I'm excited about is defending Earth. This is a project that I worked on with NASA and SETI. It's about trying to find comets that could potentially be in a collision trajectory with Earth. Currently, if there was such a comet that would be in a collision trajectory with us, we would only find out about 1 year in advance. And the idea behind the project was to find out much sooner. So in particular, we were focusing on long period comets. So these are comets that would take 200 years or more to go around the sun. And because they take so long to go around the sun, they're very, you can't spot them very frequently. So that was the idea behind it. So how could we find out sooner if there was a potential long period comet in a collision trajectory with Earth? So the main goal was to look for comets, but the first question is where to look. And as you know, space is a big place. So what we did is that first we know that when comets go around the sun, they start when they start coming close to the sun, they start ejecting some of its matter because of the high temperature of the sun. And then when Earth passes by the orbit of the comet, so for example here we see an orbit of one known comet, and as you can see there's a lot of debris that that it's released. So when Earth, here this little blue dot, passes through that orbit, some of that debris burns into our atmosphere, and that debris that is actually, we see it as meteors. So meteors actually offer a clue for where comets might be that we haven't seen before, that we don't know trajectories of. So in order to do that, we started, NASA and SETI collected lots of data around the world. So in all these star spots, you would see, excuse me, you would see where cameras are installed. So in many places around the world, there were amateur astronomers. They had cameras on top of their rooftops, and these cameras are constantly recording the night sky. And the idea behind it was to try to detect every meteor that would burn in the atmosphere. So this is what the cameras look like on such rooftops. So these are, houses of amateur astronomers that have these cameras on top, and they are just basically collecting all this data. But the problem was that they actually had to sift through all this data to try to find the meteors. So instead of doing that, we automated the whole thing. So basically this is what meteors look like. They actually look very pretty in the sky. So this is again the debris that burns into our atmosphere, and some of that debris is actually material that has been ejected from long period comets, and these are the ones that we want to find out. But first we need to find out basically all the meteors, because they're the clue. And so basically we built a convolutional neural network and an LSTM, which is a long short-term memory network, to try to find out automatically whether there are meteors or not meteors into all these recorded data. And this is what the meteors look like. They can be like really small, really bright. They can be behind clouds and so on. And there could be things that actually might look like meteors but are not meteors. So this is what a plane would look like when recorded in such cameras. This is what birds look like, clouds and so on. So basically that's just a cool application that allowed then astronomers to ease the burden on analyzing such large amounts of data, and we use deep learning to sift through that data. So that's a cool application, I think. Another application that I've worked on is for recycling. So, um, recycling is a very important job um, that that allows us to to keep our planet clean. And it is a very important job, but it's also a very difficult job. So here you will see some of the workers actually sifting through our garbage basically, and kind of sorting it, and spending a lot of time and taking out the valuable materials and so on. So it is a hard job. And at Grey Parrot, which is a startup that I worked for, we wanted to automate that. And so basically what we did is that we put cameras on top of conveyor belts, and then we would monitor all the waste that would pass through recycling facilities in order to sort them much easier. So here's a little clip on what our object recognition looks like. These are some of the materials or some of the objects that we can recognize. So again, this was work that I did at Grey Parrot together with the whole team. But it's very exciting to see deep learning actually being employed in many industries and having such impact. So this is why we're talking about it. So the next application is about generative AI. So you've probably heard about ChatGPT and large language models. So I just wanted to show you how, for example, I've used it, which I think it's pretty cool. So for example, I have a daughter who is 3 years old, and I want to write children's stories for her. So I asked ChatGPT to write me a story that would be inspiring, where the main character would face challenges, but through cleverness, imagination, and kindness and grit, the character would solve the problems or the challenges. So yeah, and then it gave me some like outlines of storylines, which I thought they were very cute. The little gardener who faces challenges with the weather, or the helpful friend who helps the neighbors to tackle different challenges by creating a community, or the lost teddy bear who has to they have to find the teddy bear and so on. So I thought it was super cute and super nice. Then I asked ChatGPT because I really liked the one that is the little detective. So I asked ChatGPT to actually write the whole story. So ChatGPT actually wrote the story, The Mystery of the Missing Cookies, and I really liked the story, and this is something I can totally read for my daughter. So once upon a time in your neighborhood, there was a clever and curious little girl named your daughter's name. One sunny afternoon, she overheard whispers among the neighbors that someone's delicious homemade cookies had mysteriously disappeared, and so on. So the little girl has to actually be a little detective and find who did it. So yeah, I thought it's really amazing. And then I also asked ChatGPT to give me a prompt to generate an image for my story, and ChatGPT made me this nice prompt, and I used this prompt to generate this other image for on Playground.ai. All right, so hopefully I've convinced you that deep learning is this really cool, amazing technology that has given us many incredible applications. But how does it work, or how do we learn? So first, let's look at how we learn as humans. So here's a challenge. So if I showed you all these images, and I told you that this is a tufa, this is a tufa, and this is a tufa, can you pick out all the other tufas? So you might pause the video and just look around and see if you can find all the tufas in the other pictures. So for me, for example, I think that this might be a tufa, this one and this one, for example. These don't really look like tufas. But like different people would have different opinions, but in general we might all agree that a tufa is something that has some sort of head, stem, and roots. And we only need to be shown a couple of examples, and we as humans generalize and can identify other tufas. So however, in order for us to actually encode this information, into a machine. So how shall we tell a machine these are the tufas, these are not tufas, and so on? How can we tell that to a machine? So that is a challenge that we need to go about. And to do that, first let's see how computers see. What computers see when they actually store an image. So a computer stores an image in an array, also known as a tensor. And it's an array that has height, width, and normally 3 channels. The 3 channels are red, green, and blue. And usually they're stored, the pixel intensities of each pixel is stored in a number between 0 and 255, as 255 being a really bright pixel and 0 being a completely dark pixel. So yeah, so this is what an image is stored like in a computer. So if I showed you this array of numbers, can you tell what this image is? So obviously we would look at all these numbers and we actually don't know what it is. But this image indeed is the picture of this cute little dog. And this is what's called the semantic gap between the way the image is actually represented on the computer and what the image actually represents as a concept. So how do we bridge this gap for machines? How can we teach computers? So if I were to give you an image and I told you to classify it as, a set of labels, can you think of an algorithm or a series of steps that you might write into this function? Is there a series of computations that you might take in order to process this image? So a lot of people have tried to solve this problem by kind of inventing or making up different ways of processing these numbers. But what has worked really well in the recent years is using the machine learning approach, which is also the approach of deep learning. But I will show you a bit of the differences later on. So the machine learning approach consists of first collecting a large data set with labels. So similar to how I showed you where the tufas are, and I said, okay, this is a tufa, this is a tufa, and this is a tufa. For a machine, we also collect lots of data and we label them. In the case of the tufa, would be tufas, but if you had labels that you actually cared about, then you would label those. Then you train a model. After you train the model, you make predictions on new data that your model has never seen before, and you evaluate the model. And this is how you can always be collecting new data and training new models and so on. So one example of such data set is this CFAR10, it's called. It contains 50,000 training images. Each image is very small, 32 by 32 pixels by 3. And so it has 50,000 images for training and 10,000 images for testing. And it has 10 different labels. So airplane, automobile, bird, and so on. And so every image is well cropped and it depicts or shows the object that the label has. So it's a small enough data set that we can play with, and we will play with, but it's also big enough to start seeing some interesting patterns. So this is just one example of a data set. There are many more data sets. One website that I really like for finding data sets, it's paperswithcode.com, and there you can really find thousands of data sets that might suit your interests or that might make you or inspire you to start playing with some of it. So there's, for example, ImageNet, which is a very, very large collection of images, hundreds of thousands that have around 1,000, I think it has 1,000 different labels. And there's many more. So there's object detection, there's lots of others. And there's also textual data and so on. There's also, on the same website, paperswithcode.com, there are also many different tasks, and it also shows you the state of the art of papers that have been published that actually work on the specific task that you might care about. So something you might check out. All right, so now that we have a data set, we need to train a model. And I just want to point out that in the traditional machine learning approach, people would spend a lot of time trying to extract features. Um, so features are things that we think are informative about an image that could then be used to train a classifier that would then classify the image, for example, into 10 different classes for in the if we're using the CFAR10 dataset, for example. So some of the features that have been used in the past have been, for example, the color histogram. And you can imagine this is an informative feature to have because if you know the predominant colors within an image, it gives you some information about what could be in the image. So in this case, frogs tend to be, many frogs tend to be green. So if green is a predominant color or a very frequent color, it gives you some information about, what is in the image. Skies tend to be blue and so on. So color is a useful feature to have. Another feature that had been used in the past is the histogram of oriented gradients, which is, a technical term to say that we are trying to detect shapes in the image. And obviously having shapes in the image or recognizing shapes in the image is also useful because different objects have different shapes and it tells you what the objects are. But without going into so much details or so many details about these features, the point being is that it used to be that machine learning, we spent a lot of time hand designing the features, thinking, okay, these are informative, these will allow us to then classify, and then training would only happen after we would design these features. And training would be a very shallow training based on the features that somebody had come up with in the past. But the whole point about deep learning is that we forget about the features that had been handcrafted, and we let the neural network or the algorithm actually find out by itself what these features should be. So instead of training on top of handcrafted features, we actually train the model end to end. So given the input and some outputs, we train an entire model that would first extract some features from the image, convert this image into different blobs, and then finally output the classifier or the classes that we want. And this is the example of image classification, but the same thing applies for many other things. So this input here is an image, and we're trying to classify it, for example, into 1,000 different classes. But it could be a piece of text, so a sequence of text, and you want to predict the next word. And this is how, for example, GPT is trained on. It could also be a time series where you give it, the prices of a certain stock in a certain window of time, and you want to predict, the next day's price, for example. So basically the same principles apply again and again and again. But the whole point is that instead of trying to handcraft the features, coming up with color of histograms or extracting shapes, or in the case of time series, trying to come up with variations in the signal, the standard deviation, and things like that, you just let the algorithm actually learn the features themselves. And we're going to see how this is done, but I just want you to have that intuition that deep learning is so powerful because instead of having humans design what these features should be, we let the algorithm actually learn the features by themselves. That is the intuition I would like you to have at this point. And this is similar to what we saw with the TUFAs, right? When I gave the example of the TUFAs. So we can look at a couple of examples of TUFAs and generalize immediately. So our brains automatically extracted what the features were. Okay, it has some head, some steps, some stem, some roots, and so on. But it automatically knows what these features should be. And so this is the same in deep learning, is that we are letting the algorithm figure that out by itself. Another cool thing about neural networks or deep learning is that it works a bit like Lego. So you put layers on top of each other and you build your algorithms this way. Here's this example is from one of the original convolutional neural networks that actually made amazing progress in the field of computer vision. Is that you have layers of computation that transform the image sequentially, and this image is transformed in such a way that at the end it gives you, some probability distribution of what the labels should be. So the layer part of it is a very important feature, and is a very composable feature in the sense that you can stack them up as Lego. So if you understand how some of these layers work, you actually can stack them up together and create more complex models. So that's also really interesting. And because it has this feature of layering on top of each other, it also has the potential of learning feature representations that are hierarchical, meaning that, for example, early hidden layers or early layers in the network would learn simple edges, simple edge detections. So, for example, here you're just detecting little blobs of edges, but further or deeper layers into the network would then compose this into contours and shapes, and finally objects. So there's a compositionality to it that, because it's built as layers on top of each other, it allows us to then learn these hierarchical features that would be useful throughout the depth of the network. So you can imagine that having these different edges at the beginning are very useful for many different contours and shapes, right? And the same, having these contours and shapes are very useful for actually detecting or identifying objects. So this is actually a very, very cool feature of deep learning. Okay, so now we will dive into the more, a bit of the math behind it. It's going to be very high level, but hopefully gives you a good intuition of what these algorithms are doing. So we're going to work with perhaps the most basic neural network. It is one hidden layer. It has one hidden layer. And again, a neural network is nothing but a function that transforms an input into some output that is meaningful to us. That's it. But obviously this transformation is where the magic happens. So here, for example, we would have an image. Imagine that this is an image from the CIFAR10 dataset, which has 32 pixels by 32 pixels, for example, and then 3 channels, and that would actually come up to 3072 elements. So you can unroll all those pixel values and put them into a vector of dimension 3072. And this is the input to your network. And then you're going to do you're going to apply some function to it, such that you convert it into a set of 10 numbers, which are the 10 classes of CIFAR10. In this case, for example, airplane, cat, dog, frog, just 10 of these from your data set. Excuse me. What I want to show you here is that actually the computations that go into a deep learning model are actually quite simple. And as I said, because you're built on top of each other, if you understand the fundamentals of what the layers are doing, you can then create very complex models just by putting them together. So here we're going to have as I said, one hidden layer neural network. So this is the input X. X is going to be multiplied by a matrix W1, and that's going to give you a vector, and we're going to call that vector well, we're not going to call it anything right now, but it's a W1 times X. Then you're going to apply a nonlinearity, meaning that every number in this output, if it's greater than 0, you will keep it. and if it's smaller than 0, you will make a 0. So this is what this max is doing. So it's just a very simple computation. And finally, we're going to multiply by W2, and we're going to get F2. And this is it. This is the computation that we're going to do. There's really, there's nothing else to it. This is the simplest neural network, and it is a building block for making more complicated ones or more complex ones. And yeah, here we go into a lot more detail. So again, so we're going to have this vector that has this dimension 3072. So 3072 rows and 1 column. And we are going to have W1, which is a vector, so which is a matrix that in order to be able to multiply it by the input x, it needs to have 3072 columns. So if you remember from linear algebra, so in order to multiply these two things, these two dimensions have to match. And this dimension of 3072 in this case is given by the data. So imagine we're working with CIFAR10, which again these are images that are 32 by 32 by 3. And so this number we can't change. However, this number 100 is something that we choose. And this is going to turn out to be the size of the hidden layer, and you are actually free to choose this number. But usually you would take something from an existing architecture to get inspiration, but this is something you can totally experiment with. So in this case, we're going to have 100 dimensions on the hidden layer. So that's the first computation, and here it's just going to give us a vector F1, which has 100 times 1, so 100 rows and 1 column. The next computation, as I said before, we're going to apply it a nonlinearity, and this is again a very simple computation where you just take every number in this vector in F1, and anything that is greater than 0 you keep, and anything smaller than 0 you make it 0. And this is how you obtain the hidden layer. These are the values of the hidden layer H. So you've effectively transformed your vector X into a new vector H that is smaller and has been, transformed by this matrix W1. And that's all you've done so far. And you're going to repeat this just so that the dimensions actually match, so that you would actually get your 10 classes that you're interested in. And then you have W2, so basically you're going to multiply W2 times H, and H, as we said, is 100 by 1, and W2 has to be 10 by 100, 10 because you have 10 classes in your CIFAR dataset, and 100 because we've already defined that our hidden layer has 100 elements. So finally we're going to get 10 numbers, so F2 is a vector of 10 numbers, so 10 rows and 1 column. And yeah, this is it. This is the computations we do for a simple one hidden layer neural network. Obviously here we have not yet learned anything, so the magic here is that we need to choose W1 and W2 such that when we do this operation, the values of F2 are such that it actually allows us to distinguish, a cat from a dog, an airplane from a ship, and so on. So the question is, what should W1 and W2 be such that F2 is actually informative? Okay, so that's the next question we're going to tackle. How do we find W? As I said before, so in deep learning, basically we're transforming an input into some output. So in this case, we have the image of a cat or any other image. We apply a function and we convert it into this output of predicted labels. In this case, we're trying to see if it's a cat, a dog, a ship, or an airplane, and so on, based on our data set. This is one example of such a function. This is the simplest neural network that you can have. And we've done all the operations to show that this is a very simple computation. So this is the function that we are trying to convert the image with. Later on, this function will be more complex and it will have, more layers and so on, but the main principle is the same. It's a conversion from input to outputs. Usually, just a bit of terminology, computing this is usually called the forward pass. Sometimes you also compute a bit more than this, but this is usually the forward pass. And so that is what you have. But initially, when you first start your algorithm, you're going to choose W1 and W2 randomly. So you're going to assign random values to these matrices. And obviously the output that you will get will be random as well. You have not learned anything at all. W1 and W2 at this point are completely meaningless, in the sense that they are not helping you distinguish anything. They're not helping you come up with the right labels for the input. But it's important to know that so W1 and W2, which I'm going to call W in general, so all the parameters of the model, actually encode the knowledge of the network. So if you have W1 and W2, all the parameters and also the operations that you make, which is the architecture of the network, then you basically have the knowledge of the network. So this is also a bit of something to keep in mind. So the values of these matrices are the things that actually encode the information. Okay, so we started with some random W1 and W2, and we get some random output that is actually not meaningful at all, and it doesn't really represent anything. However, because we have annotated data, for every image that we do this computation in, we actually have the true labels as well. So we're going to compare the output of our model versus the true labels that we have. We will compare it and we will compute something called the loss function. And the loss function is a way to measure the errors that we make. So if we are too far from the truth, this value will be high, and if we're close to the truth, this value will be low. So it is a measure of how much error we are, how much discrepancy there is between our predictions and the truth. And then the next step is to correct W. So initially W is just very meaningless, but the next step is to correct W in a direction where we would, the next time that we compute this, we would come a bit closer to the true labels. And to do that, we're going to compute something called the gradient of the loss with respect to W. And the gradient of the loss with respect to W is actually a vector that points into the direction where the loss actually decreases the most. Actually, the negative gradient is a vector that points into the direction of a local minimum of the function. And if we have this value, we will then update the weights in this way. So the previous weights, initially just random, are going to be nudged or moved in the direction of the gradient. So basically we're going to add or subtract these values, and that's going to give us the new weights. And we're going to do this many times. This is what's called gradient descent, and we're going to do this many times until we converge, until we have found a local minimum of the function. Let's look at that into more detail. So here, how do we find W? So again, we have a function which is the loss function, L, L depends on the parameters. Here, because we only can show graphically 3 dimensions, it's a 3-dimensional graphic, but you can imagine that here you have many doubles. So all the values of the matrices that you were using are actually on this manifold, on this special structure. And the loss is a function of all of them. But let's imagine for simplicity that there's only 2 values, W1 and W2. And the loss depends on these 2 values. And as you can see, the loss has peaks and valleys. And what you want to find out is what is a good local minimum such that you reduce the loss, such that you reduce the discrepancies between your predicted values and the truth. So you want to reduce the errors basically. But because you have this function, you can do this again using stochastic or using gradient descent. So initially, when you first start, when you first assign W1 and W2, you will pick them randomly. So you could start, for example, where this dot is. And using gradient descent, you will step down this sort of mountain. You will step down the mountain until you reach some local minimum. And this is what this is how you learn W basically. Yeah. Okay, so to recap. So the main idea of deep learning is that we have some input. We want to transform it into some output that is meaningful. In this case, we could have an image and we want to say the label of the image. It could also be some piece of text and we want to predict the next word. It could be a time series and we want to predict the next value of the series and so on. So it's just a transformation. So this function can be a very simple function or it can be a very complex function. But in any case, it is a function that's just transforming the input into some output. And initially, so the weights or the parameters of the model actually encode the knowledge of the network through the series of computations. So these values are the thing that we want to find out when we're training our model. And how do we find out? Well, first we initialize them randomly, and our predictions are just rubbish. But then we compare our predictions with the true labels, and we compute the average errors that we make, or the amount of errors that we make. And we also compute the gradient of this function, of the loss function, with respect to the weights or the parameters. And then we move the parameters in the direction of the negative gradient. And we do that over and over again until the parameters converge or the loss function does not change anymore. So we've achieved a local minimum. And in that way, we have reduced the amount of errors. So every time we make a new forward pass, or every time we make new predictions, we're in theory improving or making better predictions over and over again. And yeah, this is how we learn. So it's I feel like it's very simple ideas behind it, yet they're very, very powerful, as you have been able to see from the applications and the things we've talked about earlier. So just to give you an idea of the performance and the power of deep learning that in computer vision it has had. So up until around 2012, so before 2012, so this was the error rate that was being made in the ImageNet competition, which is a computer vision competition where there were hundreds of thousands of images that we had to classify based on 1,000 different labels. And up until then it was 28%, 25% are error rates. But in 2012, when the first convolutional neural network actually, or the first, I would say, The first deep convolutional neural network was implemented, the error rate dropped dramatically. And then after that, it kept dropping and dropping and dropping, based on having more layers and just having more depth in the networks and so on, until we're actually on par or very close, or sometimes better than humans at this task. So it is a very, very powerful technique, and I hope you are inspired to learn it. And in summary, we've gone through some applications. We've gone over how we teach machines to see the world, and we went over a lot of the details for a simple neural network of one hidden layer. I've showed you some of the progress that has been done, and hopefully this has inspired you to learn more about it, to pursue it, to actually apply for jobs on this, because it's a very exciting field. And hope to see you next time. So next time we're gonna do coding. We're gonna code this simple neural network, and hopefully that's exciting. So let me know what you think in the comments, and have a lovely day.